Hi, this is Jon Cross with Ohio Lumex. In this video, I'll discuss some of the features and applications for SO3 sorbent traps. First, we'll go over several of the key advantages sorbent traps have over other methods in general. Then I'll give a summary of the SO3 trap sampling procedure, some example data from SO3 measurement projects, and a few things to keep in mind when choosing how and where to sample. This video is designed to serve as an introduction to SO3 sorbent traps, not as a comprehensive user's guide. If you plan to use SO3 sorbent traps, I suggest you contact us so we can go over the details of your application and ensure you will be successful. Before discussing SO3 traps specifically, let's go over some of the core concepts of sorbent traps generally. The concepts I'll describe on this slide cover all of the Ohio Lumex sorbent trap methods that are modeled after EPA method 30B. This includes sorbent traps for mercury, ammonia, SO3, hydrogen halides, selenium, and arsenic. These sorbent trap methods are designed to be sampled directly in the sample gas and sampled simultaneously in co-located pairs. The standard sorbent trap contains two sections of sorbent material. The first section, labeled S1 in the diagram on this slide, serves as the primary capture section and is where we expect all the target analyte to be collected. Our laboratory can also spike this first section with a known mass of the target analyte to allow for a field spike recovery run, which I will explain shortly. Section 2 is always made of the same sorbent material as Section 1. Section 2 is the breakthrough section and serves as a means to determine whether the target analyte has broken through Section 1 during sampling. Every type of sorbent trap has its own unique set of sampling parameters, including temperature, flow, acceptable vacuum, and sampling duration. We will go over specific sampling parameters in a few slides. Each sorbent trap is handmade and can be customized in a variety of ways to meet the needs of a specific application. The robustness of Method 30B and all methods designed to emulate it is rooted in the built-in QA/QC. That is to say, the method includes several self-validating performance criteria. This includes pair agreement, breakthrough, and spike recovery. Good pair agreement simply means two sorbent traps sampled at the same time in the same location produce nearly the same measurement within a defined range of acceptability. Similarly, a good breakthrough measurement is one where on any individual trap, the ratio of analyte mass collected on Section 2 to analyte mass collected on Section 1 is very low, or below a defined threshold. Finally, spike recovery is a measurement of how much of a pre-spiked mass has been recovered from Section 1 of a sorbent trap. It is used to verify the performance of the combined sampling and analysis of the test method, as defined in Section 13 of Method 30B. Spiked traps should be sampled alongside an unspiked trap in order to perform the spike recovery calculation according to method. Let me give you a quick example to clarify how this works. Let's say you're sampling two traps, which we'll call traps A and B. Trap A has been spiked by our laboratory with 50 micrograms of the target analyte. Trap B has not been spiked. You sample exactly the same gas volume through both traps, send them to our lab, and we analyze them. We find that trap A has 90 micrograms, while trap B has 40 micrograms. This is a perfect spike recovery because the difference between the traps is equal to the spike mass, 50 micrograms. Ohio Lumex has focused on developing sorbent trap methods because they provide several advantages over older methods, particularly methods that require the use of impinger trains such as methods 26, 29, 8A, and CTM 027. Sorbent trap sampling equipment is much more portable than these impinger-based methods, since the required equipment is much more compact. A complete trap sampling system can be assembled within a couple of minutes, and a sampling technician can move the entire system from one location to another in a single trip. The sampling procedure is much simpler than older methods, mostly due to the convenience of sampling through a dry material in situ rather than extracting the analyte into a condenser coil or series of impingers, which must then be rinsed and prepared for the next run. The use of performance-based QA/QC criteria, particularly pair agreement and field spike recovery, provides a solid advantage over impinger-based methods. Using sorbent traps, the sampling technician does not need to deal with the hassle of using acids or other liquid reagents on site. Finally, sorbent traps were designed for use in nearly all sampling environments, including those upstream of particulate control devices. This sets the traps apart from impinger-based methods, which often fail in these environments. Let's move on to discussing the SO3 sorbent trap specifically. First, I'll highlight some of the key points regarding this method. The SO3 trap was developed to provide an alternative to the controlled condensate method known as CTM13 or method 8A. This method was designed for craft recovery furnaces, not for sampling near SCRs at coal-fired power plants. Although there are some ways to modify the controlled condensate method for sampling gas with a high concentration of particulate matter, controlled condensate still struggles to perform well in these environments. In 2019, several utilities funded a project with the Electric Power Research Institute to compare the sorbent trap method with controlled condensate in a controlled laboratory setting. The study found that the sorbent trap method provides accurate measurement of flue gas SO3 concentrations, while the controlled condensate method is subject to loss of analyte on various sample surfaces upstream of the condenser coil, as well as breakthrough of the condenser coil itself. In order for the sorbent trap method to be used as a compliance method, it has to go through a Method 301 validation. Ohio Lumex is currently working on this to allow our customers to use sorbent traps for compliance with emission limits. Right now, the primary applications for SO3 sorbent traps include evaluation of acid gas control, such as dry sorbent injection, measuring SO2 oxidation across an SCR, measurement of sulfuric acid in stacks, and determining the impact of SO3 on powdered activated carbon used for mercury capture. I'll go into some of these applications in the next few slides. The most common application for SO3 sorbent traps is to measure SO3 before and after an SCR. The SCR will naturally convert some SO2 to SO3, and if concentrations are high enough and gas temperatures low enough, the SO3 and sulfuric acid will combine with ammonia to form ammonium bisulfate, or ABS. ABS sticks to the surface of catalysts, reducing its overall surface area and therefore its efficiency. It also condenses inside air preheaters, causing corrosion and pluggage. Many coal-fired units around the country have been required to run at very low load for extended periods of time, which exacerbates ABS formation due to the reduced operating temperature. The ABS formation temperature is a function of several variables, including ammonia and SO3 concentrations. Essentially, if SO3 concentrations can be reduced, it is possible to run a coal-fired unit at a lower minimum operating temperature without creating problems for the SCR and air preheater. One of the ways to reduce SO3 concentration is to use DSI, or a dry sorbent injection. A typical engineering study using SO3 sorbent traps involves sampling at the inlet and outlet of an SCR while injecting DSI upstream of the SCR, then varying the DSI injection rate to determine how much SO3 is removed at each rate. This sort of test allows plant operators to know how much DSI is required to reduce ABS formation temperature to an acceptable level, thereby enabling the plant to run at a reduced load. Switching now to the graph on the right, we have several correlation curves between SO3 concentration and percent removal of mercury by using 3 different rates of activated carbon injection, or ACI. The effect of SO3 on mercury mitigation is clear. At higher SO3 concentrations, ACI is less effective at capturing mercury. SO3 competes with mercury for active sites on the carbon, and at sufficiently high enough concentrations, it can render the carbon barely effective at all. This is another application where SO3 sorbent traps can be used in conjunction with mercury sorbent traps. This is especially useful at facilities where both DSI and ACI are employed, and operators want to minimize material costs by optimizing injection rates. In many cases, better mercury capture can be achieved not by increasing ACI, but by increasing DSI to reduce SO3, thereby increasing the effectiveness of the ACI without changing the amount of carbon being used. Another common application for SO3 sorbent traps is to simply measure sulfuric acid emissions at a power plant stack. There are also continuous emissions monitors for this application, but for short-term testing, a monitor may not be a cost-effective solution. The dataset provided here is an example of a short-term measurement project to determine sulfuric acid emissions at a stack with 6 sorbent trap pairs sampled in one day. Sulfuric acid mist contributes to opacity, and at sufficiently high concentrations can result in blue plume. A few SO3 sorbent trap stack measurements can help plant operators know how much sulfuric acid is contributing to opacity and how close they are to having a compliance problem. Note, due to the lower temperatures compared to SCR locations, sampling in the stack requires isokinetic sampling equipment. We'll go over the sampling equipment, including the Isokinetic sampling kit, in the next few slides. Let's move on to discussing the sampling equipment used to sample sorbent traps. We've created a separate video that goes into this topic in much greater detail, so be sure to check that out for more information. The Ohio Lumex sorbent trap sampling system is called the OLM30B, and it essentially has three core components, including a stainless steel probe, desiccant canisters, and a sampling console. The probe includes two trap liners for traps with a 10 mm outer diameter, a cooling air inlet, a stack thermocouple, and a 750 watt heater. The cooling air inlet is very important for most applications, as I'll explain in the next slide. The desiccant canisters remove water and acid gases from the sample gas stream to protect the console. And the sampling console features two mass flow controllers and two pumps. For most sampling scenarios, sorbent trap runs will take about 30 minutes. However, I recommend you contact Ohio Lumex to determine the ideal flow rate and sample duration for your application. When sampling SO3 sorbent traps, it is critical to maintain trap temperature within a narrow range between 200 and 230 degrees Celsius. Sampling outside this range may result in either low bias or breakthrough. As discussed earlier, these traps are often used at the inlet and outlet of SCRs, which at a coal-fired power plant is generally around 280 to 350 degrees Celsius. In order to get the trap temperature down into nominal range, compressed plant air needs to be supplied to the cooling air inlet of the probe. The problem is, pushing cold air through a probe that is constantly being heated by duct gas creates a situation where the probe is not at a uniform temperature. Therefore, a standard built-in trap thermocouple is not likely going to measure the real temperature of the sorbent, even if it's only a few inches away from the trap. Additionally, it can be very difficult to find the right amount of cooling air to ensure a stable probe temperature while sampling. To solve these problems, Ohio Lumex has developed a fine temperature control kit for sorbent trap sampling. The kit includes an inline thermocouple, which rests inside the trap liner and measures temperature just a few millimeters behind the sorbent trap. It also includes an airflow control system to adapt from plant air to the probe and allow for fine control of cooling air. When sampling upstream of a particulate control device, as is often the case when sampling near SCRs, it is necessary to filter the sample gas entering the trap. Particulate matter may contain sulfate compounds that will bias the results, or it can completely plug a trap and prevent sampling. When there is a need to filter sample gas, Ohio Lumex generally prescribes one of two methods for filtration. Let's discuss those methods. Static prefilters are the default filtration method and will work for the majority of sampling environments. The static prefilter is essentially a plug of inert material placed into the trap. Static prefilters sit flush with the tip of the trap, and since the duct gas moves at a high velocity across the surface of the filter, there's very little opportunity for particulate matter to accumulate. These filters are put into traps during the production process, so there's no additional work for the sampling technician to do in the field. The sampling procedure is the same as it is without static prefilters, making this the easiest filtration method to use. For locations with extremely high particulate matter, especially immediately downstream of a DSI probe location, inertial filtration may be required. Inertial filtration relies on the inertia of high-velocity particulate matter to separate particulate from gas. Essentially, each sorbent trap is fitted with a custom-made inertial filter and eductor. The eductor uses compressed plant air to pull sample gas across the surface of the filter at an extremely high velocity. Simultaneously, the sampler pumps pull gas through the filter and into the trap. The suction created by the pumps is not powerful enough to overcome the inertia of the particulate, so it escapes the filter and goes back into the duct. Some applications, such as measuring sulfuric acid in a stack, require isokinetic sampling. In low-temperature environments like a stack, SO3 will have converted to sulfuric acid aerosols, which behave like particulate matter in a gas stream. In order to capture a representative amount of these aerosols, the sampling method must be isokinetic. To those not familiar with this term, it means the sampling trains must be fitted with specially designed nozzles, and the gas must be sampled in such a way so as to ensure the velocity of gas flowing through the nozzles is equal to the velocity of gas in the sampling environment. This method ensures the traps collect the same ratio of aerosols to gas as is present in the flue gas. The dew point of sulfuric acid depends on SO3 concentration, temperature, and water concentration. As you can see in the graph on the right, and as you would expect, dew point increases with both percent water and SO3 concentration. When the flue gas conditions are below the dew point of sulfuric acid, the equilibrium shifts towards sulfuric acid aerosol. Under those conditions, isokinetic sampling is required to get an accurate measurement. I won't go into detail on how the sorbent traps are analyzed, but I'll highlight a few key elements. When you send your SO3 traps to our lab, the sorbent sections are separated, dissolved in water, and analyzed by ion chromatography. The analytical method uncertainty has been measured to be approximately 5%, and all method performance criteria draw direct parallels with method 30B. To expand on that a bit further, that means all calibrations and calibration verifications must meet specified performance criteria within 10% for the results to be reported as valid. Let's recap some of the essential points discussed in this video. First, the SO3 sorbent trap method provides an alternative to the controlled condensate method and continuous emissions monitors. Sorbent traps are cost-effective, easy to use, and provide excellent data quality. SO3 measurements are critical for understanding ammonium bisulfate formation and are often used to evaluate the effectiveness of dry sorbent injection. ABS reduces SCR efficiency, creates problems for downstream instrumentation, and can cause pluggage and corrosion in air preheaters. When using activated carbon injection, it is important to know how much SO3 is present in the gas. SO3 competes with mercury for active sites on activated carbon, which can render ACI less effective. If the need arises to measure stack emissions of sulfuric acid mist, SO3 sorbent traps provide a fast, cost-effective method for doing so. The sampling method is a bit more complicated than sampling upstream of an air preheater, but is far simpler than controlled condensate or a continuous monitor. Finally, the SO3 sorbent trap is a trusted method of measuring SO3 because it is modeled after method 30B, the reference method for mercury. The sorbent trap method includes built-in QA/QC to ensure high-quality measurements, including pair agreement, breakthrough, and spike recovery. Thank you for watching. If you have any questions about SO3 sorbent traps, visit our website or contact me directly. I would be happy to help.